graphing this, we want to consider all the things you would consider in graphing a normal function, all the stuff that you knew of before calculus, and then the stuff that you have gotten to learn as you're learning calculus. You want to look for these things, critical points, where it's increasing, where it's decreasing. So we mentioned that the domain of this is all real numbers. Domain is negative infinity to infinity. There's something else that you can notice about this one if you're pretty good with your college algebra. X to the fourth minus 8x squared plus 8. If you were to substitute in negative x, well, negative x to the fourth and x to the fourth are going to give you the same thing. Same thing with your squared term. In other words, this is an even function. What does it mean that it's an even function? What's the graph of an even function looks like?
Symmetrical.
Yeah, it's going to be symmetric with respect to the y-axis. So, symmetric with respect to the y-axis. All right, great. There's another little easy thing that I can get when I look at this, and that is, say, the y-intercept. What's the y-intercept of this graph going to look like? 8. Yeah. F of 0. That's a nice easy 8. So 8 is going to be about there, maybe. Okay, great. Let's move on to the calculus and see if we can't try and attack some of this graph using the calculus. What's the first thing you think I'll do when I apply what we know for calculus to this?
Take the derivative.
Take the derivative, sure. So f prime of x, Sophia, what's f prime of x going to equal for us, please?
4x minus 16x.
Yeah, 4x cubed minus 16x. Perfect, perfect. What do I want to do with this derivative now? Any suggestions?
Set it equal to 0.
Set it equals 0. Yeah. So let's take a look at 4x cubed minus 16x equals 0. Oh boy. I know we've got a quadratic formula. There's actually a cubic formula and a quartic formula, but a young mathematician by the name of Galois proved that there's no formula for the 5th degree polynomial. And then he was killed in a duel the next day. Yeah, at age 21. Yeah, I know, that's hitting home. What's that? Yeah, you can factor out the 4. In fact, let's factor out the 4x, which leaves behind x squared minus 4 equals 0. Thanks, Adrian. Let's go a little bit farther. 4x times x minus 2 times x plus 2 equals 0. So, okay, looking good there. Now what? So I get x equals what? What are my choices for x? 0, 2, and negative 2. Those are the places where the function can change signs. And that function is really our derivative. So let's do ourselves a little table here. So example A. And I hope that you're getting comfortable with these tables because I like seeing them. They help me make sense of your work. So x, f, f prime. Got negative 2, 0, and 2. Make sure you put these across your number line up at the top in order. Otherwise, it's going to really mess you up. All right, so here. So at these points, You have a derivative of 0. Okay, that's wonderful. And what else? What else? I need to figure out if the derivative is positive or negative in between these things. Now, do you need some help with that, or what do you want to do? Do you want to do that on graphing calculator or thought experiment? What works for you?
I think it's fun.
Just thought experiment? Okay. Let's think about putting in kind of a bigger number out here, like a 3. If I put in a 3, I'm going to put it in here. 4 times 3 is 12. And then 9 minus 4 is 5. So you have a positive times a positive. Yeah, you're going to get something positive here. If you put in something between 0 and 2, like a 1, then right here in this expression I'll get a negative times a positive. That's going to be negative. And then it's going to follow through with that pattern. Polynomials often, not always, but often follow this pattern. So great. What's that telling me about my function here? Decreasing, increasing, decreasing, increasing. So in particular, let's see, what kind of a point does this have to be if the function is decreasing and then starts increasing? Local min. How about at 0, what do I have? Local max. And finally a local min. Okay. Let's keep going. We've got our first derivative. Let's calculate the second derivative. So the second derivative, f double prime of x. Let's go back up here. I don't want to deal with the factored version of this. Let's go back up here. That's going to be 12x squared minus 16. Uh-oh, this could get ugly. 12x squared minus 16. I want to set that equal to 0 and solve. Because there's no x term, I guess I would do it this way. X squared is going to be 16 over 12, which is going to reduce to 4/3. What does x equal? Plus or minus 2 over the square root of 3. Not particularly nice numbers. Okay, not much you can do about that. But numbers that we got to work with nonetheless. All right, so let's do another little chart here. X, F, and F double prime. So putting these in order, that'd be negative 2 over the square root of 3 and 2 over the square root of 3. And then over here. Once again, you kind of need to test some points. You can plug this into your calculator. I think we can test this without necessarily going too crazy. 2 over the square root of 3, I'm not sure what that is, but I'd bet that it's less than 2. Or, you know, if you really want to be safe, it'd be less than 4. If I put in a 4 here, 16 times 12 minus 16, well, whatever that is, it's going to be positive. What's an easy test point for in between here?
0.
0. Plugging in a 0, 0 minus 16, that one's easy. So positive, negative, positive. Great. Looking at that. What's this tell me? Ugochi? Let's just tell me that the second derivative is positive here.
Concave up,
Yeah, thank you so much. Concave up, and then what?
concave down. concave up.
Perfect. Concave up, concave down, concave up. So, now I've already put a few points on your graph for you. So if you're curious, this one is the square root of, or excuse me, -2 over the square root of 3. And here's 2 over the square root of 3. But we've got to fit all this together in a nice symmetric graph. One thing this is telling me is that this graph is concave up until I get to right here. So how could I fit that in? Well, the function's decreasing until I get here. This has to be a local min. So, all right, let's see if we can't draw something that brings all this information together. So it's going to be decreasing until I get to here. So it's going to look like that somehow. And then it gets there, it bottoms out, it has a minimum at -2, and then it starts increasing. And I'm going to have it increase until I get to this point. Now it's still increasing until it gets to this point right here, 0.8. What's going to change right here?
It's gonna go down.
What's going to go down? The concavity is going to change, right? It goes from concave up to concave down. So even though it's still increasing, the concavity changes. Now I claim that we've done all the hard work here at this point. Why am I right in saying that?
It's symmetric to the y-axis.
Perfect. It's symmetric to the y-axis. If you're clever enough to spot the fact that you have an even function to begin with, then, all right, the rest of your work is done. It's gonna, you have to pardon me, I hope I don't give you vertigo or something. It's gonna come down here, and then continue over here. And finally, it's gonna go up. So, beautiful. There's your function. And of course, along the way, you've got increasing, decreasing, concave up, concave down. These are your inflection points. Right here, inflection point. Local min, I've already got. Local min. And that would be your local max. There's no global max in this because the function keeps going up forever. You could also call these absolute mins, but I'm not going to worry about that distinction at the moment. Kyrillos, did you have a question?
Well, I was just gonna say, aren't those absolute minimums?
Yes, they are. Yes, James?
So when we have to state the, where the local maxes and mins are and the inflection points, do we only state the x value or the limit, the amount that it reaches to?
I guess it depends on how they ask the question. You could be asked for either piece of information. Typically speaking, I try and be very clear about what I'm looking for.
Yeah.
A lot of times I'll put on the test, I want the y coordinate, or maybe I want the x coordinate.
Okay.
So it's a difference between where it is, which is the x coordinate, and what it is, which is the y coordinate, at least in my opinion. That's the way I see those things.
Thank you.
You're welcome. Thank you. Anything else? Let's move on to example B.
Question.
Yeah. Oh, yeah.
So like, for this graph specifically, can I say that the local Are them absolute min, is those two local?
Yeah, these are absolute mins, yes.
Like that's the same thing if I write that on the top.
Yeah, in this case, they're both absolute mins.
Okay.
You'd be right in saying that.
Alright.
Now, when you first look at this, it's tough to know that this is an absolute min versus a local min. So that's why I'm just in the habit of writing local min there. But in further reflection on this graph, if the graph is coming down to here and then goes up, one of these would have to be a local, an absolute min.
Okay.
At least one of them. And because it's symmetric, they're both absolute mins. Okay, let's take a look at example B. So we've got y equals x squared plus 5x over 25 minus x squared. Let me just do something to maybe make things more visually striking. Let me rearrange the denominator. Typically speaking, you write things with the highest degree term first, the next highest degree term to the right of that, and so on in decreasing order. Why do you think I'm trying to draw that to your attention right now?
Both have a
X squared.
X squares can cancel.
They don't really cancel. You can't cancel these.
In fact,
They're- it shows the limiter.
Yeah. It's because we're eventually going to look at the limit, right? Now, for starters though, let's look at one of the more prominent features about this graph, which is the domain. Because this is a rational function, because you have a denominator, you could run into some problems. And the places you're going to run into those problems is where the denominator equals 0. In other words, what values?
5 and -5.
Nice. Thanks, gentlemen. Appreciate you giving me both answers there, a positive and negative square roots. So your domain is, well, one way to write it would be negative infinity to negative 5, union 5 to, negative 5 to 5, and then from 5 to infinity. That'd be one way to write it. But there's something else important and special about this graph here. Does anyone know what's special again it's going to happen at 5 and negative 5?
It's your vertical class.
Yeah, you can have a vertical asymptote. So let's see. Yes, I do have. All right, so there's the first one. So let's take a look at one more thing before I turn on part of this graph. So you have vertical asymptotes. Where the denominator equals 0, so at x equal 5 and x equal negative 5. How about your horizontal asymptote? If you didn't know what it was, or if it wasn't as obvious, how would you have to calculate your horizontal asymptote? Limit as x approaches infinity of x squared minus, or x squared plus 5x over 25 minus x squared. So here's a good review question for you. In calculating this limit, could I do this with L'Hopital's rule? If you plugged in the limit, you would have infinity over negative infinity. So yeah, you could, but it would actually take 2 iterations before you get to the limit. What's the faster way to do this limit?
take the
Take the
coefficient.
limit.
It's the leading coefficients, right? You've got a 1 here and a -1 here. 1 over -1 is -1. Done. So, but please don't give me this. So your horizontal asymptote is really y equals -1. So when you give me the equations for asymptotes, if you just give me -1, I'll probably mark it wrong. Not that I'm trying to be mean, it's just that you can't graph -1 by itself. You have to have an equation. So here's our horizontal asymptotes. Here's our horizontal asymptote, here's our vertical asymptotes. And I think that's on our graph. Yeah, right here. So we can put in y equals -1. And let's see. And I put in, well, we got to be kind of careful here. Let's look closer at this function. Because actually I'm wrong on one of these things. And I'll show you why. Let's look at y equals x squared plus 5x over 25 minus x. In the numerator I can factor out an x.
X squared.
Let's just factor out the x times x plus 5. In the denominator I can factor that as 5 minus x times 5 plus x.
So there's a hole.
And even though they're not perfect, they're close enough. Those things kind of cancel out as long as x is not equal to -5. As long as x is not equal to -5, this function and this function will be the same. So it gives you x over 5 minus x as long as x is not equal to -5. So what's going on at -5?
It's a hole.
There's a hole in the graph.
Wait, shouldn't it be 5?
No, at 5, see the -5 term canceled out. So that just means that this is undefined at -5.
Okay.
But here at +5, you'll be dividing by 0, and we can't divide by 0.
Okay.
At -5, you have 0 over 0, which, all right, that's undefined, but at least you can work around it. Now, if you wanted to find the hole in the graph, again, you could actually use L'Hopital's rule. So a while ago, we had to do this in a different way. We had to spend some time with analyzing the graph, taking a look at the limit from the left, limit from the right. But here, if we wanted to, you could use L'Hopital's rule. So limit as x approaches, let's see, where was it? -5 of x squared plus 5x over 25 minus x squared. If I try to plug in the limit, I get 0 over 0, so let's use L'Hopital's rule. Limit as x approaches -5, that'd be 2x plus 5 over -2x, yeah, -2x. Okay. Is that any better? If you plug in -5, in the numerator you get -10 plus 5, which is -5. What do you get in the denominator? 10. So the hole Yeah, negative. So the whole is at -5 and 1/2, or -5 and -1/2. There you go. That should be where the hole is in that graph. Now, there's nothing to say that you have to do all this work in a vacuum. It's not like I'm going to take your graphing calculators away from you on the exam. So let's just take a quick look at it. I'm going to look at it with Desmos because their graphs are way better. Let's see. No, that's the wrong one. There we go. So here's what you should be getting out of all this work here for the graph. You've got a horizontal asymptote at here at -1. So that's there. You've got your vertical asymptote here. And the other important thing that you're going to need to see is that you've got a hole right there. That hole, as you approach from the right or approach from the left, you see you're getting close to, but not quite touching that value of -1/2. Let's finish this one up. Now, in this particular problem, and I've done this before on exams, so if you see that, then just be happy that I must have been in a good mood when I wrote the exam or something like that. But I actually gave you the first and second derivatives. In particular, the first derivative is y prime is 5 over x minus 5 squared. All right, let me switch over here. I need to know where this can change signs. And this can change signs where the numerator equals 0 or the denominator equals 0. Can the numerator equal 0 anywhere?
Excuse me, no.
I wonder if the mic picked that up. All right. The numerator can't equal 0. How about the denominator? Can the denominator equal 0?
5.
At 5. So in order to try and see what's going on with this function, we're going to make ourselves the same little chart that we made in some of our other ones. And that is something like this. X, F, F prime. And then I can put in a 5 here in the middle. 5. Now the function and its derivative don't exist at this point. So here's a fancy symbol. It's a backwards capital E. That means there exist. And if I draw the universal not sign through it, that is a little slash, that means that point doesn't exist. There's no derivative at 5. There's no function at 5. But we can test either side. But if I put in something in here and I square it, I'm always going to get a positive number. So it's positive and positive. Joe K,
Yes.
what's that telling me about my function?
Increasing and increasing.
Increasing and increasing. Great. I also gave you the second derivative. So the second derivative is y double prime was equal to -10 over x minus 5 cubed. And we're going to do the same thing. The numerator can't change signs at all. So this can change signs only at the denominator. Okay. So x, f, f double prime. You still have to check on both sides of 5 for the sign of the second derivative. Kind of like the first derivative, the function doesn't exist here, nor does its second derivative. But I am gonna see a difference in signs. If I put in like a 6, 6 minus 5 is 1, cubed is still 1, divided into negative 10. Negative divided by a positive is negative. If I switch to something like a 0 or a negative, or excuse me, a 0 or a 4, what I'll get when I subtract that from 5 and cube it is a negative number. A negative divided by a negative is positive. You can just test points in this function if you put it in your calculator. But that's telling me a little bit more about my function. That is, the function has to be concave up and then concave down. All right, let's put all that together. You can do this on your graphing calculator. Your graph should match this. You can see that the function is concave up here, concave down here. It's approaching its asymptotes, so looking good there. Looking real good. All right. So let's see, 5. Comments or questions on that one? Definitely I would want to see the hole in the graph on something like this. So I think that would be right there. And then the graph, roughly speaking, would look like this. Here. I probably would appreciate if you show me the correct y-intercept. In this case, I got it wrong because the y-intercept really should be here at 0. All right. I'm not going to do it, but I am going to show you one last little thing about, say, a problem like C. And you've maybe finished off C at home. The challenge with C is playing around with the derivative. So example C. G of x is x to the 5/3 minus 5x to the 2/3. One thing you're going to have to convince yourself of is of the domain. Essentially, these denominators represent cube roots, and you're not going to have problems taking a cube root of a negative number. So you're okay there. The domain is going to be negative infinity to infinity. But I'm worried about you and your calculation of the derivative, and in particular finding the critical points. The first derivative looks like this. 5/3 x to the 2/3 minus 10/3 x to the negative 1/3. Okay. And you can calculate the second derivative without too much problem. G double prime of x is going to be 10/9 x to the negative 1/3 plus 10/9 x to the negative 4/3. But like I said, the challenge is going to become in setting these things equal to 0 and solving. So finding, actually it's more than just equal to 0. Because the critical points are going to occur where the derivative is 0, but one other type of point. Where else are they going to equal 0, or where else are you going to get a critical point? Derivative 0 and or the derivative doesn't exist. So, all right, so there's two sets of points we've got to take care of. Let's play around with this derivative. So g prime of x, 5/3 x to the 2/3 minus 10/3, and I'll have an x to the 1/3 here. I'd like to be able to combine these, but I can't, because they don't have common denominators. What am I missing here that I don't have here? I need an x to the 1/3 term there. So one thing I could do would be multiply by 1. I could multiply x to the 1/3 over x to the 1/3. In the denominator, that's going to make me pretty happy. All of these are going to have the same denominator, 3x to the 1/3. In the numerator, what happens with these two things?
It just becomes a as x.
Yeah, if you add the exponents, you get x to the 3/3 or x to the first power. So g prime of x equals 0 is going to be where the numerator equals 0. And that's where 5x minus 10 equals 0 or x equals 2. Where does the derivative not exist? Yeah, at 0. The derivative doesn't exist at 0 because you'd be dividing by 0. So something interesting is happening at the graph at 0. Either you have a vertical tangent or a cusp. And you can look at the graph and finish this up to decide which. All right, that's all we got time for here.